So welcome to complement probability. We are going to look at A being an event and then let A bar be its complement event. So the author says A bar, he reads it as the complement of A. I read it as not A. So if we look at this, the probability of A plus the probability of not A would have to include all the possible outcomes in your experiment. So the sum of those two probabilities has to be 1. So you can always subtract either probability over and say, well, in this case, the probability of not A or the probability of complement of A is equal to 1 minus the probability of A. So if we had 5 flips and you want to find the probability of at least 1 tails, first thing you got to do is find the denominator. So in that previous example, we had 3 flips, which was 2 to the 3rd power, which was 8. Now it's 2 to the 5th power, which is 32. And I have no desire to build a tree diagram with 32 endpoints and make up 32 individual outcomes to find my sample space. All right, that's a lot of work. And on top of that, once you find all that sample space, they would want you to find the probability of 1 tails, the probability of 2 tails, 3 tails, 4 tails, 5 tails. No, I don't think so. Way too much work. So let's think of the opposite of at least 1 tails. All right, well, the opposite would be no tails or all heads. So if you think about it, wait a second, go back to that original tree diagram with 3 flips. At the very top, there's only one way to get all heads. So that's going to be 1 out of 32. So 1 minus the probability of 5 heads is 1 minus 1 over 32, which equals 31 over 32. So the sum of these 5 probabilities up here equals 31 over 32. Doesn't matter how we get to that sum. You could add all 5 together, or we can be sneaky and do this complement probability where all you got to do is subtract 1 probability from 1 and you got your answer. So again, keyword at least 1 or at least something is a dead giveaway that you want to use complement probability. All right, next example, in a group of 10 people, what is the probability that at least, oh my gosh, there it is again, at least 2 people have the same birthday? We're going complement probability. I'm not going to find the probability that 2 people are the same, 3 are the same, 4, 5, 6, 7, 8, 9, and 10. I'm going to take the opposite of at least 2 people. That's nobody has the same birthday. So they're all different. So the complement is the probability of all different birthdays. So if I go 1 minus the probability of all different birthdays, I'll have the probability of at least 2 people having the same birthday. So find the sample space, 365 days. Find the total number of outcomes. I keep getting those two confused. There are 365 days in a year, and every day is likely to occur. So to find the size of the sample space, got to find all different birthdays. There's 10 probabilities that are going to have a denominator of 365. Oh, wait a minute. Let's simplify that. How about 365 to the 10th power? That looks better. Okay, now I left some space here because if you look at the first person, that first person has all 365 possible days available. Put that in the numerator. Second person, well, they can't have the same birthday as the first person, so they only have 364 days available. Put that in the second fraction. The third person, okay, has to be different than the first 2. They only have 363 days available. Put that in the third denominator. And so you notice, hey, all my denominators, they keep reducing by 1. So 362, 361, 360, 359, 58, 357, 356. And lo and behold, I think, wait a minute, time out. This is an arrangement. Order matters. First person, second person, third person. This is a permutation type 2. Nothing can repeat. It's an arrangement where order matters. So I can say n is 365, r is 10, and in the numerator I can put 365 permutation 10. I don't have to multiply this all together. I can let the calculator crunch this out. But wait, we just got to take this and subtract it from 1. So 1 minus the probability of all different birthdays is 1 minus the minus 365 permutation 10 over 365 to the 10th power. So I'm going to go to my calculator and type it in. So if you have an older type of graphing calculator and you don't have the fraction icon that you can have show up, then we got to put parentheses around the numerator, divided by parentheses around the denominator, we'll subtract it from 1. If you do have the newer calculator, then I would recommend that you use 1 minus alpha y equals. Use your fraction command because now you don't have to use parentheses. 365 math, go over to probability, permutation number 2, put in 10, go to the bottom, 365 raised to the 10th power, and we can hit enter. And you still get the same decimal. All right? So there's my probability. Oh, right there. Back up. Boom. I always get that blue screen when I put something over that presentation. Sound good? All right. Our next probability that we're going to look at is, again, another very useful probability. It's called binomial probability. This is where you take all your outcomes and you break it down into two possibilities. What I want and what I don't want. Kind of like complement probability. All right? So, if we force everything to have two outcomes, success or failure, then all we have to do is we have to figure out how many successes and how many failures are going to be possible. So, we're going to let n be the number of trials, r will be the number of successes, let n minus r be the number of failures. We're going to let p be the probability of success of one trial, and q be the probability of failure. So again, here's your complement probability. 1 minus p equals q. So the binomial probability formula looks like the following, and it's going to look familiar. This is your binomial expansion theorem. All right? They just switched around two things being multiplied together, but it doesn't matter. You will have your combination, the number of trials, and your R is the number of successes. Your probability of P is your success raised to the R power, because that's how many times we want the success to happen. But then Q is your failure, and then N minus R has to be how many times your event failed. Okay? This is great when there's only two categories. Good and bad, boys and girls, true and false, whatever. Just make sure that the sum of the two probabilities is going to add up to be 1. So for example, let's say the Spirit Club is 75% girls. What is the probability of randomly picking 5 people where there are 3 boys and 2 girls? To be perfectly honest with you, that's going to be a low probability. You want to pick more boys than girls, and yet there's 75% girls, which means there's 25% boys in the Spirit Club. So 5 people, that's your N. Combination 2 will let the girls' probability be our success. 0.75 for the probability of girls raised to the power of 2 times the probability of boys, 0.25. There's going to be 3 boys picked in that grouping. So now we just go to our calculator, crunch this out, and we come out to be 0.08789 if I round it to 5 decimal places. So again, 5 combination 2 times 0.75 squared times 0.25 cubed. There's your probability of that happening. And again, if you think of this as a percent, that's just under 8.8% chance of happening, which makes sense because you have 75% girls and you're trying to pick more boys and you have more girls to choose from. Okay, next example. A manufacturer has determined that a bulb machine will produce one bad bulb for every 2,000 bulbs it produces. Okay, that means the probability of good is 1,999 over 2,000. Probability of bad is 1 over 2,000. So this is a good setup for complement probability if we need it. So what is the probability that an order of 200 bulbs are all perfect? Okay, so the probability of good is 1,999 over 2,000, and we want 200 to be good, all of them, so that's this probability to the 200th power. And that's going to come out to be 0.9048 if we round it to 4 decimal places, just over 90%. All right, what if there is at least one bad bulb? Okay, there's that phrase, at least one. That's my complement. So 1 minus the probability that they're all good. So 1 minus the 0.9048, 0.0952. All right, things we've seen before. Now, how do we get to our binomial probability? Is one they ask for specifically 1 bad bulb, 2 bad bulbs, 3 bad bulbs. All right, there is 1 bad bulb. All right, so now we're going to say the probability of R being good, R will be our success. All right, so that's going to be 199 good bulbs, and we're going to have 1 bad bulb. So 200 combination 199 good times the probability of good over 2,000 raised to 199th power times 1 over 2,000 raised to the first power. Now, I took a screenshot with my old calculator. This is what I would do for these probabilities. I strongly recommend that you just take the individual probability and store it for G, for good. And there's the probability as a decimal. The 1 divided by 2,000, I stored it in B. All right, there's my decimal. Don't worry about it if it's in scientific notation. So when I go 200 combination 199 times, now I can just put in G to the 199th power times B to the first power. Here is my probability that that's going to happen, 0.0905. If I wanted to find what's the probability that there's going to be 2 bad bulbs, exactly 2, then, all right, we're going to change 199 to 198 that are good. So 199 becomes 198, this power becomes 198, and this power of 1 becomes a 2. So that's what I want to enter in my calculator. So again, I would probably just hit second enter, take this copied down statement, change 199 to 198, 199 to 198, and change this power to a 2. So as you can see, I changed the 199s to 198, the 1 has a power to a 2, and there's the probability, 0.0045. Just less than 1%. Or I should say just less than 0.5%. So if you think back to our Christmas lights that you possibly buy, when you buy a string of 100 or a string of 200, you will notice that in the string of lights, they always have 2 replacement bulbs. Because what's the probability that you're going to have 2 bad bulbs is less than 0.5%. That's why they don't put 3 in there. All right? there is a 9% chance one is bad, but only a 0.5% chance that two will be bad.